Hello, I'm Anna Mackay and today we'll be solving trigonometric equations algebraically. There's quite a bit to this, so let's get on with it. Just a refresher in terms of solving, thinking about when sine of x is equal to 1. That means the vertical component is at 1 and that happens at pi on 2. But as we know from the unit circle, I guess it just keeps going round and round and round. So for the period of sine, it's 2 pi. So that means every 2 pi, sine of x is going to be equal to 1. And the way we signify that is that x is equal to pi on 2 for every k lots of 2 pi. So that represents all of the periods, so multiple periods, and where k belongs to z, and z is from the family of integers. Okay. And also a refresher on what the unit circle looks like, that on the left we have the pi on 4 family, which is the 45 degrees, and on the right we've got the pi on 6 family. So all the different combinations that we can have for that, for sine and cos. Write them down if you don't already have them down. Next, getting into solving some examples. So if we're asked to solve for x on the domain from 0 to 2 pi, the cos of x equals negative root 3 on 2. So every one of these questions I would encourage you to draw a unit circle and visualize where cos is negative root 3 on 2. For me, I know that that's the pi on 6 family. The way I prefer to think of it though is I think of which one's a half first. So if cos is not a half, therefore sine must be a half. And when is sine a half? Up here and down here. Just depends if we're after positive or negative. We're after negative cos though. So the two quadrants that could be are here and here. So let's draw that in, and we're in, so sine is a half, so cos is root 3 on 2. So we're looking at here and here. What are they? That's how many lots of 6 to get round to there? That's 5, 6, so it's 5 pi on 6, and underneath here, 7 pi on 6. And so the way we write that out is we're solving for x. X is equal to 5 pi on 6. And we can write a comma or, and 7 pi on 6. So it's a matter of visualizing where that's happening in the unit circle. And that's all you need to write for your answer, because we're in that domain there. It's restricted. Here, what if we are solving for this? Basically, you need to move all the numbers to the right-hand side to know what you're dealing with. So you would add 1 and divide by 2, and you're solving for when sine x is equal to a half. Okay, we can do that. When is sine of x equal to a half? So sine is the vertical. So when sine is a half, we've got the two options that could come out from here. So they've got to line up with when sine is a half, here and here, positive a half. So that can happen for the pi on 6 family. Forgive my drawing there, it's not very accurate, but that is 1/6, knowing that the second 6 would be up there, 3, 4 and 5, pi on 6, and there are two answers for the domain that we're after. So your answer is when x is pi on 6 or 5 pi on 6. Alright, getting a little bit harder now. Tan. First of all, let's rearrange so that we have the numbers on the right hand side when tan of x is equal to negative root 3. Now, up until now I've been doing a lot of work on sine and cos, so they're probably coming quite quickly to you. But what about tan? I guess there's three things that could happen. You've got the pi on 4 family, which is when sine and cos are both 45 degrees, and so if you write sine on cos, you're going to get them equal, and so you're just going to get versions of 1 or negative 1 for tan. That one I'll leave you to work out. But the one that you'll need to think about is when you're getting root 3 or 1 on root 3 and positive or negative combinations of those. So I guess a quick sidetracking here. If you had root 3, how could you get that from the root 3 on 2 and the half combinations? It will come from when it's root 3 on 2 as the numerator and a half as the denominator. Think about how that's rearranged like that. That would simplify down to root 3. And then think about different positive and negative combinations you could have for that. So that was when sine is root 3 on 2 or it might be easy to visualize when cos is a half. And the other combination is 1 on root 3 that you could have for tan, and that would come around from when the root 3 is in the denominator. So the cos is root 3 on 2. As you can see, this simplifies, flip and multiply. The 2's cancel out, that's 1 on root 3. So if tan is 1 on root 3, that meant the cos had the root 3 in it, or sine was a half. So back to our question at hand, tan, we're after negative root 3. So that must mean this first combination. But for me to visualize, I find it easier to think about the half. So when is cos a half? That is for the x component. So cos being a half is here and here. So we're looking at either here or on this side. But for tan to be negative, you think about cast or old silly turtles crawl. Tan is positive in quadrant 3 and quadrant 1. So we want negative tan, so therefore we're after quadrant 2, this one here, and quadrant 4, this angle here. And what are they? They come from the pi on 6 family. So we've had 4 6 to get around to there, or that's also 2 pi on 3. And coming around here, how many 6 that we've had? We've had 10, but that simplifies down to 5 pi on 3. So answering your question for when tan of x is equal to negative root 3, it's when, have I even written it down properly? No, but essentially it's 2 pi on 3 and 5 pi on 3. Next, solving for cos when there's a square here. As we know, putting the square there is the equivalent of putting cos of x all squared. So to undo that operation, you square root the other side. So you're essentially solving for when cos of x is equal to 1 on root 2. However, account for the plus and the minus. So thinking about when is cos positive or minus 1 on root 2, that's the pi on 4 family, which is the 45-degree family. So we're thinking about this. And positive and negative. So we need all of those into account. So I guess the first one we've got here is pi on 4. Then over here we've got 3 pi on 4, 5 pi on 4, and what's the last one? 7 pi on 4. So just remembering that that comes from when cos is, oops, not that one there, 1 on root 2 is those versions there. And the way you write that out is x is equal to all of these, and you write them as a list. And 7 pi on 4 is our last one. Next, if we're asked to solve for x for cos is 2x, now this is where we have to take into account our domain. Instead of being an x here, it's 2x. So the way you account for this is you think about what your domain is that you need to end up with. But instead of an x, what have we got? We've got 2x. So write 2x there. And you think, well, what have I done to x to turn it into 2x? I've doubled it. So you have to double both ends of the end point for the domain. And then work it out cos of x. Well, when that's equal to 1 on root 2. So when is cos equal to 1 on root 2? That's it, the pi on 4 family. And positive cos here, that we're after these two quadrants there. And they are pi on 4 and 7 pi on 4. And so we start writing that out for 2x, but, okay, hang on. So that's equal to pi on 4 and 7 pi on 4. However, what we've worked out is that we need to take it into account for 4 pi. So over here, the 2 times that cos is 1 on root 2 is pi on 4, coming around and around, and then 7 pi on 4. That'll get us to 2 pi. But we need to account for 4 pi, so we need to go around again. So we've got 2 pi and we're adding on 1/4. So how many quarters have we got now? We've got 9 quarters, if you like. And you go round and round and round. And what is this one? The second time around, it's 7 pi on 4 plus 2 pi. That would give you 15 pi on 4. So they're the 4 for the domain for 2x. And now what you do to get your x answer is you're dividing everything through by 2. finishing with 15 pi on 8, and they're your 4 answers for x within that domain now. All of those fit in 2 pi. Next one, a sine example here for x divided by 2. So you start with the domain you've been asked to end up with, and you think about, yes, but my sine is not x now, it's x divided by 2. So for each of those endpoints, you divide them by 2, and that's the angles you have to take into account. So you think about your unit circle. When is sine of x now equal to root 3 on 2? Well, that's the pi on 6 family. And for sine, that's up here at, I guess, 2 pi on 6 or pi on 3, and then also here. So that root 3 on 2 is there, which is about, what is it, 0.86? So 2 pi on 3. Now we have to take it into account for pi, and that's fine, it'll be those two there. So write that out, that's actually x over 2 will be equal to pi on 3 and 2 pi on 3 in the domain of pi, or 0 to pi. And to finish it off, you multiply each of these by 2. And there are 2 answers to fit in the domain of 0 to 2 pi. And our last one here, finding exact solutions. So it's a little bit different now. We've got a sine and a cos. So the one technique to try for this is think about tan, how that's equal to sine on cos. So could we rewrite that with sine on cos? Well, you could divide through by cos and then divide the other side through by root 3. Imagining that 1 would be left in place of the cos, not a 0, as some people are often tempted to do. So this is our new equation, and we're trying to find, well, when is sine x on cos x equal to 1 on root 3? So that's asking us when tan of x is 1 on root 3. And we talked about that earlier, that if you've got the root 3 on the bottom, that's when the cos has the root 3 on 2 in it. When does cos equal root 3 on 2? That is here at pi on 6, and being positive, when's the other time? We want tan being positive. When's the other quadrant that tan is positive? Over here. And that would be when, so that's our cos is root 3 on 2, and there root 3 on 2, very approximately. So you write out that x is those two, but go back and read the question. It actually wanted it for the domain in degrees. So we have to transform these radian answers into degrees. Just remember that pi is equal to 180, and essentially you can substitute that in. Where you see pi, write 180 and divide it by 6, and the answer that you would get is 30 degrees, and the other answer you'd get is 210 degrees. Okay. Make sure you like it, subscribe to the channel if you haven't already, and next we'll be using trigonometric functions, so some actual real-world applications of all of this stuff. Thank you.